Hi everyone, this is a problem from Griffith quantum mechanics. It's on Weyl theorem. So it shows that d by dt expectation xp equal to 2 expectation of kinetic energy minus expectation of product of x and differentiation of v with respect to x, where t is your kinetic energy and h is equal to t plus v. So in a stationary state, the left side is 0. Why it is so? And then if it is so, then we will be having expectation of t will be equal to x dv dx expectation, and this is called Weyl theorem. So use this theorem to prove expectation of t will be equal to expectation of v for the stationary state of harmonic oscillator. So now for solving this, we know expectation of any operator with if we differentiate any operator q, this is given by I by h cross expectation of commutator of Hamiltonian with respect to this operator plus partial differentiation of this operator with respect to t. So this we will be applying it here and solving this equation. So d by dt, in place of q we can write xp, so I h cross, h is Hamiltonian, in place of q we are going to write xp, right? And since xp is not dependent on time or explicitly dependent on time, you can consider this as 0, right? So this we can write it as I by h cross expectation commutator of h comma x then p, right? By breaking x and p plus again Hamiltonian, we have p, and then outside we can write it as x, and then again expectation bracket close. So we will be finding these two, this and then this. So firstly let us find h comma x commutator. So Hamiltonian can be written as momentum squared by 2m or momentum operator squared by 2m plus a potential which is dependent on x comma x. So this is equal to, we'll break this into 2, p square by 2m comma x plus potential v comma x commutator. So here we will be getting, this is x and this is a function of p. Here p square is a function of p square. So in my earlier videos I already discussed about this. When we have a function like any function of p or x, so we can write it like this. It is a function of p, we will be writing it as only p, and this is 2m is constant 1 by 2m, so we can take it out. So 1 by 2m, we will be writing here p, and in place of x we will be writing x, right? We will write here p and then x, and then we will differentiate this p square or function of p with respect to p itself, right? And then since here the potential is a function of x, so this will be like, if we write it x comma x, then we will differentiate that function that of x with respect to x itself. But commutator of x comma x will give you 0, so this term is 0, so we are left with this. So we can write this 1 by 2m, and p and x commutator will give you minus I h cross, since it is reverse, is it? And this will give you 2p, differentiation of p square with respect to p. We will left with like minus 2 will get cancelled, I h cross, then you left with here m, and then p over here, right? And then we have the next term, we have h comma p. So here we can write same thing, p square by 2m plus v, then we have p over here. So we'll break it out, we'll break it in same form, the same manner. So here we can see p square comma p, a function of p square with p will be again 0, so we can ignore these two terms and we can write only v, which is a function of x comma p, right? So this will give us, let me make it like this. So v is x, since it's a function of x comma p, and then we are going to differentiate this function of x v with respect to x itself. So we'll be left with x and p commutator will be IH cross, right, and dv dx, right? So here we have 1 and this is 2. So we'll replace this value here, so we'll be getting, therefore the dd dt of x p, the product of xp expectation value will be equal to I h cross, then we have this term, h comma x commutator is given by minus I h cross by m into p, and then we have p over here, so it will be minus I h cross by m into p square, right, plus we have h comma p, that is this value, so I h cross, and we have x over here, so x dv dx, right? If we take out I h cross common, and obviously we can take minus as well as common, because I with I will give you -1, so minus and minus we can cancel it out, and we will be left with p square by m, right? And if we take minus common, we will be getting here minus x dv dx, right? Because we take h as common, right? So this can be written as p square by m minus x dv dx. So ultimately we can write it is, if you multiply by 2, so this I can write as 2m minus x dv dx, right? Or we can write 2, and this can be written as kinetic energy p square by 2m, and here is x dv dx, right? So we have already shown this. Then the next they have said why it is in case of stationary state the left side, this term is 0, why it is so, since in stationary state so what we have, our expectation value of any operator, like expectation value of q, or it may be x, it may be p, for stationary state will be always independent of time, is independent of time. So this term will be 0. So we will have, what is this? This is dd of x into p expectation. So if this term is 0, we will be having 2t will be equal to x dv dx. So this is nothing but Viral theorem, which is a very important theorem, and we will be using this theorem for proving this for stationary state of harmonic oscillator, right? So we can find this. We have for harmonic oscillator we have potential equal to half m omega square x square, right? Then we can find directly this, or we can find dv dx. So if we find dv dx, we will be getting half m omega square, there will be 2x, differentiation of x square, right? And we will be left with m omega square x, right? So now then x dv dx, if you multiply this function with x, you will be left with m omega square then x square, right? This also can be written as half, right? M omega square x square, then we will be multiplying this with 2. So this is what potential V. So this can be written as 2 multiplied by V. So if we replace this with 2V, we can write 2T equal to, for this value we will be replacing as 2V. 2 and 2 will get cancelled, and we will be left with expectation value of kinetic energy will be equal to expectation value of potential energy. So thank you so much.